power equation in synchronous motors. The objectives are derivation of power equation and problems on power and efficiency also. Here, let the power equation, let it be voltage, supply voltage, that is for phase, and the armature current for phase IA, armature resistance is RA, that is in for phase manner, and alpha is load angle. Now, the input power to motor is, so motor input power per phase is V into, that means supply voltage into armature current into cos phi, VIR cos phi. Now, total input power for three phase star connected motor is P. So here power is equal root 3. Here they didn't write root 3. Here they have to write root 3 VLIL cos phi. Here root 3 VLIL cos phi. So where VL and I are on line values. The mechanical power developed, the mechanical power developed by motor, here copper losses in a synchronous motor takes place in armature winding. Armature winding. So here the armature copper losses for phase is Ia square Ra. Here total armature copper losses for three phase. Here this is for three phase, 3 into Ia square Ra, 3 into Ia square Ra. Here the motor power PM is equal to P minus PCU. That means input power minus copper losses, that gives the motor power. Next, for three phase. For three phase, the motor power is equal to, that is PM is equal to root 3 VLIL cos pi minus 3 Ia square Ra. Minus 3 Ia square Ra. Now, the power output to get the power output here to get the power output, we have to subtract the iron friction and excitation losses from the power developed. Here, the net power is equal to net power output or P out is equal to Pm minus constant losses. Here, in the synchronous motor, what are the constant losses? Here, constant losses are that equal to iron, friction, and excitation losses. So now go for power stages and a synchronous motor. Power stages in a synchronous motor. Now see here, here observe this one. Here, see, here input is for the synchronous motor AC electrical. That is, the power is electrical power is root 3 VL IL cos pi. Stator copper losses. Stator copper losses for three phase synchronous motor is 3 Ia square RA. Then after that, the mechanical power developed. So when the mechanical power developed, the armature, then iron and friction windage excitation losses will occur in the motor. So finally, after this friction losses, iron and friction losses, mechanical power output is the motor is rotating. So here we are giving the input is electrical input and getting the mechanical output. The losses are copper losses, stator copper losses, and the iron friction windage excitation losses. And the mechanical power developed is after the stator copper losses. So this is the power flow diagram. Now power flow diagram input input motor input power and stator copper losses. After that, gross mechanical power developed. Then losses are iron friction losses. After that, finally we get net mechanical power output. power input for phase in stator, that is, this is for single phase, but we want and three phase is different to 3 VLIL cos. But here phase is power is equal VIA cos phi. Next, this power is divided into two parts. So here, this power is goes to the armature copper losses, that is IA square RA, and mechanical power developed in armature, that is EB IA cos alpha by, that is EBIA cos alpha minus pi. Here, the mechanical power is going to two ways. One is for this mechanical power developed in armature is going to two ways. One is for losses, another one is for mechanical power. So these losses are iron, friction and excitation losses. And next one is will come the output power, that is P out. Now power developed by a synchronous motor, except for very small machines, the armature resistance of a synchronous motor is negligible as compared to synchronous reactance. From the phasor diagram, it is seen that AB is equal to AB sin alpha, that is equal to IXS cos phi. Or otherwise, VI cos phi, that is equal to ABB sin alpha XS by XS. That is, now VI cos phi is equal to motor power input. Now see here, P input is equal to EB sin alpha by XS, that is equal to root 3 EBB sin alpha by XS. Here, this is for the three phase. Now, since stator copper losses have been neglected, the stator copper losses are neglected, P input, that means input power, also represents the gross mechanical power developed by the motor. Now Pm is equal to root 3 EB V sin alpha by XS. The gross torque developed by the motor is Tg. Tc is equal to grass tower is equal to 9.55 pm by minus. So now go for problem 1. Here, to the problem. A three-phase for 40 watts 50 Hz star connected synchronous motor develops 7.46 kilowatts. The effective resistance per phase of armature winding is 0.5 ohms. The motor operates at a power factor of 0.75 lagging. Iron and friction losses are as given, that is 1350 watts. So now what they are asking, calculate the armature current, power supplied to the motor, efficiency of the motor. Efficiency of the motor. Now the solution is three-phase star connected synchronous motor. Output power is 7.46 kilowatts and 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 iron and friction losses are 1350 watts. Now the total mechanical power developed, that is equal to 7460 plus 1350. Now total PM total mechanical power, that is equal to 8810 watts. Solution mechanical power developed for phase is 8810 by 3 and PM is equal to 2936.67 watts. Now supply voltage for phase V is equal to 400 by means 440 by root 3, which gives a 254.03 volts. Now cos pi is equal to 0.75 lagging and RA is equal to 0.5 ohms per phase. Here motor input for phase is equal to this P is equal to VIA cos pi. Now armature copper losses for phase PCU is equal to I square RA and the mechanical power, that is equal power input power minus ECU copper losses, that is equal to VIA cos pi minus I square RA, that is 293.6 equal to 254.03 into 0.75 IA minus A square into 0.5. Now from this 0.5 I square minus 190.52 IA plus 296.67 equal to 0, will get IA is equal to 16.09 0.09 amps. Here, the motor input for phase P is equal to the Ia cos pi, that is 254.03 into 16.09 into 0.75, that is equal to 3065.51 watts. Now total power supplied, that is equal to 3 into motor input for phase. So that is 3 into 3065.51, which gives the 9196.53 watts. So efficiency is nothing but output into 100 by input. Now 7460 into 100 by 9196.53, that is 81.12%. Here now problem 2. So read once again it. The 75 kilowatts three-phase Y connected 50 Hz 440 watts cylindrical rotor synchronous motor operates at rated conditions with 0.8 power factor leading. The motor efficiency excluding field and stator losses is 95%. Excess is 2.5 ohms. Calculate mechanical power developed. The second one is armature current, third one is back EMF, fourth one is power angle, and fifth one is maximum torque of the motor. Have given data P out is equal to 75 kilowatts, three phase Y connected. Frequency is 50 Hz. VL is equal to 440 volts. Power factor is 0.8 leading. Efficiency is 95%. Excess is 2.5 ohms. So here the solution is signal speed Ns is equal to 120 F by P, that is 120 into 50 by 4, which is minus 1500 RPM, and the mechanical power developed PM is equal to PM. Now that is P out by efficiency, which gives at 75 into 1000 by 95. That is PM is 78,950 watts. Now the solution power input equal to Pn, that equal to root 3 VL IL cos theta. So that is root 3 440 into IL into 0.8, that is equal to 78,950 watts. So armature current IA is equal to 129 amps. Now the applied voltage for phase, that is 440 by root 3, is nothing but 254 by 254 volts, that is 4 phase voltage. Now V is equal to EB plus JXS, or EB is equal to B minus JIAXS. Now here on this we get the value 250 angle of 0 minus 322 angle of 126.9, which is 254 minus 322.9 within bracket cos 126.9 plus j sin 126.9. Here 254 minus 322 within bracket minus 0.6 plus j 0.38. The finally V is equal to 516 angle of minus 30 degrees. Therefore alpha is minus 30 degrees. Full torque occurs when alpha is equal to 90 degrees. Full torque occurs at alpha is equal to 90 degrees. The maximum output power PM 3 EB we sin alpha max 3 into 256 into 516 into sin 90 by 2.5, which is 157,275 watts. Therefore, full out torque, that is 9.55 into PM by N. So 9.55 into 157,275 by 1500, that gives the 1000 Newton meters. So here, summary, we have discussed derivation of power equation, problems on power and efficiency.